To understand how to find the basis for the column space of a matrix, it's best to see it using an example. Okay, so here we have a matrix A. We want to find a basis for the column space of A. Now, remember, a basis has to have two properties. It needs to span the space, and it needs to be linearly independent, right? The set of vectors in the basis need to be linearly independent. So I already have a set of vectors that span the space, right? These vectors here, the columns of matrix A, by definition, the column space of A is the span of these vectors. So these vectors form a spanning set for the column space of A. But I don't know if they're linearly independent. So I need to take this set of vectors and then strip out any redundant vectors, and what I'm left with should be a linearly independent set that spans the column space of A, and therefore will be a basis for the column space of A. All right? So how do we determine if they're linearly independent? Which ones are redundant? So let's call these vectors v1, v2, v3, v4, v5. Okay? We want to determine if they're linearly independent. So what I want to do is I want to look at the homogeneous equation, a1v1 plus a2v2 plus a3v3 plus a4v4 plus a5v5 equals the zero vector. I know that for a linearly independent set, the homogeneous equation only has one solution, has only the trivial solution, with a1, a2, a3, a4, and a5 all equaling 0. So I want to try solving this system and see if I get just the trivial solution or if I get extra solutions also. If I do have extra solutions, then that means I will need to take out vectors in order to get a linearly independent set. Okay. Now remember this linear combination equation, this homogeneous equation. If I were to write it in matrix form, the v1, v2, v3, v4, v5, those would be the columns of the matrix. The coefficients is the unknown vector I'm looking for, and then the zero vectors on the other side. Okay. By the way, notice this vector, or this matrix here, our coefficient matrix, is just matrix A, right? Matrix A has v1 as the first column, v2 as the second column, v3 is the third column, v4 is the fourth column, v5 is the fifth column, just like here. Okay, so this is just matrix A. So all I want to do is solve the homogeneous system. So I'm just going to have matrix A on one side, and the augmented part, I would have zeros, except I usually leave them off, right, when the augmented part is 0. So I just want to take matrix A and find its reduced row echelon form. So let's use our calculator for this. -3, -1, 2, 4, 1. And continuing on. Okay, I've got my matrix in. And now I want to take the reduced row echelon form of that matrix. And there is what I get. So the reduced row echelon form of A is equal to 1, 0, 0, -13 halves, -3, 0, 1, 0, 16 thirds, 19 sixths, 0, 0, 1, -61 over 12, -29 over 12. And then the last two rows are zeros. Okay, so this reduced row echelon form of matrix A will tell me how many solutions I have to my homogeneous equation right here. Okay, So if we remember that imaginary augmented part, all zeros over here because it's a homogeneous. If we kind of imagine it back in there, the solution that we get from this augmented matrix would be the solution set to the homogeneous equation. All right. Now, I don't really care what the solution is. I just care how many solutions there are. And we could see here, and we could see this even before we add the augmented part in, that we have 3 leading entries, but we have 2 free variables, right? Remember, columns without a leading entry in them correspond to free variables. If I have free variables, that means I'm going to have infinitely many solutions. So the set of vectors here are not linearly independent. This matrix has 2 free variables. So the homogeneous equation has infinitely many solutions. Okay. In particular, that means not just the trivial solution. If you have more than just the trivial solution, that means the vectors are not linearly independent. So the vectors v1, v2, v3, v4, and v5, the columns of matrix A, are linearly dependent. All right. We want a linearly independent set because we want a basis. So the question is, which of the columns should I take out to form my linearly independent set? Well, when getting an infinite number of solutions, what's giving us that infinite number of solutions is the free variables, because I can make those free variables whatever I want, and so I have an infinite number of solutions. And these 2 columns correspond to my free variables. Okay? If I take matrix A and I get rid of the columns that correspond to my free variables, the reduced row echelon form of the rest of the matrix would be the same. But now I don't have any free variables. And I would have only one solution. Okay? So the idea here is that once I'm in reduced row echelon form, I can really easily see which vectors, which columns are redundant to the span of the column space. In particular, the columns that give me free variables are going to be redundant. Okay? These columns, the 3 columns on the left, are going to be non-redundant vectors. I can't get rid of those. Now remember, the column space of the reduced row echelon form of A is not the same as the column space of A, but it does tell us what vectors we want. So here, these 3 are redundant because they correspond to having infinitely many solutions. They are going to give me free variables. And these 3 are not redundant and linearly independent. So what you want when determining your column space, you want to go back to your original matrix and take the same columns. These 3 columns are going to be linearly independent column vectors. And these 2 are redundant. Okay? And so our basis for the column space of matrix A is just those first 3 linearly independent vectors. So namely, my first column was what? Negative 3, 0, 4, negative 4, 6. Negative 3, 0, 4, negative 4, 6. My second column in my original matrix A -1, -4, 2, 2, 6. -1, -4, 2, 2, 6. And my last column, 2, -4, -4, 8, 0. These three columns together are a basis for the column space of matrix A. All right? So the way you're going to know it from here on out, you find the reduced row echelon form of your matrix. You look for the columns that are not free variables, which means they have a leading entry. You look for the columns with leading entries. And then you go back to your original matrix and find the same three columns. Those columns are the basis of your column space. Note this means that the number of vectors in your column space is going to be the same number of leading entries you have, okay? Which is equal to the rank of the matrix. So the rank, or rather the dimension of the column space of a matrix, is equal to the rank of the matrix, which, as you may recall, was also the dimension of the row space of the matrix. So the row space and the column space of the matrix have the same dimension. Both the dimension of the column space of a matrix and the dimension of a row space of a matrix are equal to the rank of the matrix.